Good evening, everyone, and welcome to RASC Toronto Centre Online. I'm Dr. Elena Hyde, and this is my first appearance as the second Vice President of RASC Toronto Centre. And this is our January 2021 Speakers Night presentation. Hooray! So this is actually one of two types of gatherings that we have online these days. Note that it is not at the Ontario Science Centre due to the pandemic, so we are in fact online. And later on, our president, Tom Luton, will be talking about our various programs for RASC. So tonight, I am absolutely delighted, as are we all, to welcome Professor Nassim Bozorgnia from York University to shed some light on one of the most mysterious of all astronomical substances, dark matter. Professor Bozorgnia obtained her PhD from the University of California, Los Angeles in 2012 and has held postdoctoral positions at the Max Planck Institute in Heidelberg, the GRAPPA, or GRAPPA, I hope I'm saying that right, Institute at the University of Amsterdam, and of course the Institute for Particle Physics Phenomenology at Durham University. So if we want to get a peek inside the strange world of dark matter, we are very lucky to have Professor Bozorgnia speaking to us tonight. Her research is in the field of astroparticle physics and focused on the dark matter problem. So very good stuff. More specifically, she has been developing various strategies to significantly improve our knowledge of the dark matter distribution in our galaxy, the Milky Way, with the aim of studying its prospects for dark matter searches. So without too much ado, Professor Bozorgnia, most of us are still very much in the dark on dark matter. Can you illuminate this opaque subject for us?
Thank you very much for the very nice introduction, Elena. So I'm going to tell you tonight about this mysterious component of the universe, the dark matter, and how we can search for it. So let's start by asking an important question. What is the universe made of? So if you consider all the atoms in the universe, the atoms you can find in our bodies, in planets, stars, and all the galaxies, this is all the ordinary matter that we can see or electromagnetically detect. And we have a lot of evidence that this ordinary matter only makes about 5% of the total energy matter content of the universe. 68% is made of this unknown form of energy called dark energy, which is responsible for the accelerated expansion of the universe, and we don't know much about. And the topic of this talk is the dark matter component, which is 27% of the universe. And this dark matter component does not interact electromagnetically, and we cannot see it. That's why it's called dark. Now, if we only consider the matter content of the universe, actually 85% is made of this unknown elusive dark matter, and only 15% is all the ordinary matter that we know and understand well. Now, the evidence for the existence of dark matter comes from a variety of different observations at different scales, but it also has a very long history. So already in the late 1800s, early 1900s, the British physicist Lord Kelvin thought about applying his theory on the motion of gas and molecules to the stars in our galaxy. And basically, he used the velocities of the observed, velocities of the stars to estimate the mass of the galaxy. And then he found that there are some discrepancies with the mass that you would expect only from the visible stars. And so he has a quote mentioning many of our stars, perhaps a great majority of them, may be dark bodies. So already at the end of the late 1800s and early 1900s, physicists and astronomers were starting to think about this missing mass. And actually, French mathematician Poincaré became interested in the ideas of Kelvin, and he did his own calculation. And he was among the first to use the term dark matter in 1906, of course, in French. But from that time, if we fast forward to today, we have acquired a bunch of evidences for the existence of dark matter coming from the scale of small dwarf galaxies to galaxies the size of the Milky Way to large galaxy clusters and up to the largest scales of the universe. So let's look at some of these evidences in more detail. One of the important evidences for the existence of dark matter is coming from the measurement of the rotational velocity of stars and gas going around the center of galaxies like our own. And this work was pioneered in the 1970s by Vera Rubin and her collaborators, Kent Ford. And so this was a measurement of the velocity of the stars as they go and gas as they go around the center of the galaxy. And these measurements deviated from what would be expected if the galaxy was only made of visible matter. And basically, as you go to the outskirts of the galaxy, where there's no more visible matter and there's very few stars, you still see that there is some fast motion of those stars going around the center of the galaxy. And then this basically pointed to the fact that there must be some mass where there's no more visible matter. So beyond where the visible matter stops, there's still mass. And based on this, basically after the 1970s, this picture of the galaxy that everyone was used to, which was just showing the visible part of the galaxy, dramatically changed, because now we know that the galaxies like our own Milky Way are actually a small part of the full mass of the galaxy. So basically, these galaxies are embedded in a very large dark matter halo. So we call this spherical dark matter structure, a dark matter halo. And the radius of this halo is more than 10 times the radius of the observed galaxy. And so this is a new picture that we believe that represents much better the galaxy with all the dark matter component included there. And we also think that most of the density of dark matter is in the center of the galaxy. And as we go to the outskirts, this density would also just decrease as a function of radius. Now, this picture is still not the full and most complete picture of how the galaxy looks like. So if we could see all the dark matter structure that exists in a galaxy like our own, this is what we would actually see. So here you see all these little clumps of dark matter. So this is all dark matter except the actual, the observable part of the galaxy, the spiral disk that you see in the center. The rest is just dark matter structure. And this is a result of a simulation producing this structure of dark matter. And we believe that there are many of these dark matter subhalos, so smaller structures of dark matter, smaller mass, but they're bound to the halo of the Milky Way. And this just, the reason for this is that we believe that galaxies like our own are formed from mergers and merging of multiple subhalos over time. And so they acquire a lot of structure, basically, when you consider the whole galaxy. Now, one of the other important evidences for dark matter comes from gravitational lensing. So here the idea is that if you have some amount of mass in space, Einstein's equations tell us that this mass would actually curve the space-time. And if you're looking at some distance source of light, like a galaxy which is behind this mass, you see that the light rays that are coming from this distant galaxy are distorted due to this curvature of space-time and due to this mass in between. And so you would see some multiple images of this galaxy instead of one nice image, or you might see some distortion and curvature in the image of the distant galaxy. And for clusters of galaxy which have large masses, you actually see this effect of the gravitational lensing from some distant sources. And in this way, you can figure out, based on analyzing those images coming from the distant source, you can figure out the exact mass of these galaxy clusters. And this would again be different than what you would expect if you just compute the mass based on the galaxies, the visible parts of the galaxies in those clusters. And so this is another evidence for the existence of dark matter. And here is an example of this gravitational lensing happening in the Abell 2218 cluster, which is 2 billion light years from us. And you see that distant galaxies actually are, their images, due to the effect of the gravity of this cluster, are just turned into this arced images. And then you also see multiple images of the same galaxies here appearing. And so from these observations, you can calculate the amount of dark matter in clusters such as Abell 2218. Now, another very important evidence for the existence of dark matter comes from looking at collisions of galaxy clusters. So one important example is a bullet cluster. And this is showing the effect of two galaxy clusters colliding. And if you look at what you can detect in X-ray, which is the hot gas in these clusters, you see that they are in these pink bright regions. So these are specified by pink bright here. And most of the mass of the galaxy are actually not where the hot gas is, but we can determine the mass via gravitational lensing, and they appear in these blue regions. So since we believe that dark matter is not interacting with anything else other than interacting via gravity, they would just pass through very fast when the two galaxies collide. But the hot gas has electromagnetic interactions, so it would slow down. And so this is the effect that you will see, that those two components are separated. And so you would infer that where the most mass is different than where the visible mass is. So this is again pointing to the existence of some amount of unseen mass, which is not interacting the same way as the visible mass. And this is sort of a poster child of the collision of two galaxies, but we have many others which exist, and you see the same effect. So we have a number of observations of galaxy cluster collisions, and using gravitational lensing, you get exactly the same, you can infer the same result, basically. Now, another way to obtain a very precise measurement of the dark matter abundance in the universe is looking at the cosmic microwave background radiation. So the map that you're seeing here is the remnant electromagnetic radiation coming from 380,000 years after the Big Bang. And it's really the first picture that we have of the universe. It's really an infant picture of the universe. And this is when the universe became transparent to photons. So neutral hydrogen formed and photons could travel freely, and they have reached us. And you see the temperature. So this is a map of the different temperatures from that early time. And you see some temperature fluctuations. So different colors show different regions of temperature. And this correlates with the different densities in the universe at that time. And based on precise measurements of this map, you can determine to the percent level the abundance of dark matter in the universe, and also the abundance of normal matter, and so on. And so based on this cosmological input, that the cosmological data that we have, and these parameters that we obtain, we can actually simulate the whole universe on a computer, starting from the time very close to the Big Bang, and let that simulation run until today. And we you can put the amount of dark matter that you get from the CMB, for example, the amount of ordinary matter and dark energy as inputs in this kind of simulations, and run the simulation and obtain galaxies which look a lot like our own galaxy. So here's an example of one of these simulations, the illustrious simulation. And this is starting from a few million years after the Big Bang. And here you see the density of dark matter, which is just clumping under the force of gravity. So you see that there are these dense regions shown in white forming due to the effect of gravity. And this becomes really the seeds for galaxies to form later on at those centers, gravitational potential, where it will switch in a moment to ordinary matter, and gas would actually fall into these centers of these galaxies. So now you're seeing the ordinary matter, and the different colors is just the different temperature of the gas. So gas falls into these centers, and basically the gas cools and makes stars. And so these turn into, many of these galaxies can also have a supermassive black hole in the center, and they're very active. So they would accrete the material from close to the center, and then actually just emit a lot of gas and material outside. And so if you just keep this simulation running, so this is just at 6 billion years, and you're seeing the ordinary matter here. And if you keep it running until today, you will see galaxies which look a lot like our own galaxy. These galaxies, as well as other types of galaxies that we observe in the universe, so ellipticals, irregulars, and so on. So you see a zoo of galaxies from these simulations, which look a lot like the observed galaxies, and they match a lot of the properties of the observed galaxies. So this is quite interesting because you need dark matter to produce these kind of galaxies that we observe. And this is another evidence for the existence of dark matter. So all of these evidences point to the existence of dark matter, but all of them are due to the gravitational interaction of dark matter with ordinary matter. The actual nature of the dark matter particle and its non-gravitational interactions are still unknown. So if we think about the standard model of particle physics, which you see in this table on the left, we have this make basically the ordinary matter, and you have in orange and yellow the ordinary particles like quarks, which are inside protons and neutrons, or leptons such as electron, or neutrinos, as well as these so-called force carriers, which are particles responsible for the interactions between the other particles I just mentioned. And so these are responsible for 3 out of 4 fundamental interactions. So we have the photon specified by the symbol gamma, responsible for the electromagnetic interaction. So that's the particle of light. We have the gluon, responsible for the strong nuclear force. And we have the Z and W particles, which are responsible for weak nuclear force. So strong nuclear force holds the nucleus together, and the weak nuclear force is, for example, responsible for radioactive decay. And we also have in the standard model of particle physics, the Higgs particle, which was recently discovered in 2012 at the Large Hadron Collider in CERN. And so this basically, this picture is what we have for the standard model of particle physics. But none of the particles in the standard model of particle physics can actually be the dark matter particle. And the reason is that so many of these particles are charged, but for the dark matter particle, we need a neutral particle, so it wouldn't interact electromagnetically. We want it to be massive and have the abundance that we know that dark matter has. And it should be a stable particle so that if it was produced in the early universe, still should be around today because we see all these evidence for its existence. And many of the standard model particles actually dissipate too quickly, or they disappear too quickly. They're not stable, or they're not massive, or they're not neutral. So none of these particles can be the dark matter particle. And these standard model particles make all the ordinary matter that we know. So we need to go beyond the standard model of particle physics if we want to think about a candidate for the dark matter particle. Now, theorists have been working very hard in the last few decades, and we have many theoretically well-motivated dark matter particle candidates. And some of the key questions that we're interested to answer are, what is the dark matter particle's mass? What is its interaction strength with ordinary matter? And to be able to accurately try to answer those first two questions, one other important input is the dark matter distribution in our galaxy. So these all tie together, and I'll tell you a bit more about it throughout the talk. So I'm going to focus in this talk on one particular dark matter candidate called the weakly interacting massive particle, or the WIMP. The WIMP is one of the most extensively studied class of dark matter candidates beyond the standard model, and this is for good reasons. One important reason is that if you consider the dark matter particles interacting and annihilating to the standard model particles, and when I talk about standard model particles, I just mean the ordinary matter again. If this interaction is happening via the weak force, this would automatically produce the correct abundance of the dark matter in the universe today. And so this is really one interesting reason that this might be one of the basically the dark matter candidates that might be the true dark matter, but there are many other dark matter candidates, as I mentioned as well. Now, the mass of these weakly interacting massive particles are between 1 to 10,000 times the proton's mass. And one other interesting aspect of this candidate is that we can experimentally search for them. And actually, there's a huge experimental program using 3 complementary ways to search for WIMPs. And I'll go briefly over each of them. These are indirect detection, collider searches, and direct detection. So what is indirect detection? So again, looking back at the dark matter particles interacting and giving us the standard model particles, we can use space-based observatories or ground-based telescopes to search for these resulting standard model particles. And this is the way to infer indirectly that we have, this was due to dark matter, basically. And so if you consider the dark matter particles interacting, they can produce different particles, which are one of the standard model particles. And they can go, for example, to gamma rays, which are high energy photons, so light, or they can go to neutrinos or antimatter, proton, antiproton, or electron positrons, and so on. And if we let's focus for a second on gamma rays, which is one of the important channels for indirect detection. We can try to understand what we expect, basically. If there are dark matter particles annihilating to gamma rays, this is the gamma ray flux that you would expect. This is based, again, on a simulation. And here in this simulation, what has been important is also the amount of dark matter throughout the galaxy. So as I mentioned, we believe that most of the dark matter density is at the center of the galaxy. So you have the largest effect in the galactic center, and this decreases as you go out in radius from the center of the galaxy. So this is the gamma ray flux, again, that you would expect from dark matter annihilation. But this is a very difficult and challenging business because this is, you have to try to find this flux against all the astrophysical flux of gamma rays that exists there. And so to show you how that looks, this is the sky map in gamma rays, high energy gamma rays from the Fermi satellite. And you see in this bright yellow and red points, basically, all the gamma rays that you expect from normal astrophysical sources. So for example, in the disk, you have this diffuse galactic background, which is just due to the interaction of cosmic rays with gases and photons in the interstellar medium. Or you have many of these sources are due to pulsars, which are rotating neutron stars or active galactic nuclei. So you have to find that small signal that I showed you inside this large astrophysical backgrounds that exist. So this is a very challenging task, but of course there has been a lot of studies trying to very accurately identify this background and try to remove it and try to see if there is something still remaining if you remove that background. And so far, although there has been some hints, there hasn't been any convincing signal yet from indirect detection. But in the future, there might be, as this is still there is a lot of data that has to be analyzed and methods to reduce this background. Another way to search for dark matter is to create it in the lab. So you can think about the opposite interaction that I showed you before for indirect detection. Instead of the two dark matter particles coming in and interacting and producing standard model particles, you can actually have two standard model particles which would interact and produce dark matter. And you can actually produce dark matter in the lab. And so this is being done. I mean, there are efforts to produce dark matter. Of course, again, we haven't yet we don't have a signal for it yet, but these are collider searches. And one of the important colliders that we have is the Large Hadron Collider. And this is a very large tunnel going underground, and it's in between Switzerland and France, and it's 27 kilometers in circumference. And what is happening is that there are two proton beams, and in this collider, you would actually collide those two proton beams and try to produce dark matter. And so this is a little video of what is happening in these colliders. So you actually accelerate the proton beams up to speeds close to the speed of light. So these are really fast proton beams. And these are just the boosters trying to accelerate them. And then there are 4 detectors, 4 points where you can actually collide these together and search for the effects. And so this is the tunnel underground and going in that 27 kilometer circumference. And this is a proton beam. You see the 3 quarks inside, and they would now, it will show you the Atlas detector, I believe, where the 2 proton beams coming from the 2 opposite directions would collide, and you would get a bunch of rays coming out, bunch of different particles. Now, what happens here is that the dark matter particle would be fast moving. It would just escape the detector. So you wouldn't really directly see the dark matter particle, but you would actually see that some energy would be missing. So due to the production of dark matter, and since it just left the detector, you would see its effect in missing energy. And again, this is there's a lot of data from the LHC where it has to be analyzed, and so far they haven't found this evidence for dark matter being created in the lab yet, but this is something that can happen in the future. Now, the third method to search for dark matter, and in my opinion, actually maybe the most promising way, is to look for the scattering of a dark matter particle with a standard model particle in an underground laboratory. So the idea is that we believe that billions of WIMPs are passing through the Earth every second, but they very rarely interact. And so a dark matter particle would come in some underground detector, and there's some nuclei in that detector. The dark matter would just collide with that nucleus in the detector. It would scatter away. But the effect that we're trying to observe is this tiny energy of the nucleus after it has recoiled or just moved a little bit due to the effect of the dark matter particle hitting it. So it's a scattering of the dark matter particle with this nucleus. And these are really rare event searches because we would expect much less than one event per kilogram of detector material per year. So since WIMPs are interacting very weakly, we need really large detectors, many kilograms of detectors, and now they're at ton scales. And we need to run them for multiple years to see a few events, basically. We also have to go underground. You notice that I mentioned that these are underground detectors, and the reason is that we want to get rid of background signals coming from cosmic rays and environmental radioactivity, which can mimic the effect of a WIMP. And so many of our detectors are operating several thousand meters below the Earth's surface. And so there is a very large program of direct detection experiments running around the globe since a few decades now. And you notice actually here in Canada, we have SNOLAB with a number of very exciting experiments taking data. And SNOLAB is actually Canada's deepest underground laboratory at Sudbury in Ontario. And around 2 kilometers underground, there would be a new experiment called the Super CDMS experiment, which is, you see a prototype here on the left, and this is commissioning now. And so it's very exciting, especially for lower mass WIMPs when this experiment starts to take data. And we'll have the results in a few years. So what happens if we have a positive signal in one of these experiments, let's say in a few years? So with a positive signal, we can specify to some confidence level the mass of the dark matter particle and its interaction strength with ordinary matter. And this is really great. This is what we want to answer. So this is really interesting information. But we also have to know what is the local distribution of dark matter in order to be able to specify the dark matter mass and interaction strength, because to calculate the event rates in these experiments, we're assuming there's some specific amount of dark matter coming through the detector every second. And also, it has its own specific velocities that we are assuming, basically. And so to be able to accurately determine the dark matter particle physics properties and interpret the results of these experiments, we have to have an idea of what is the dark matter density and velocity distribution before being able to answer this question. So this is really like trying to find a needle in a haystack. There are tiny interaction rates in these experiments. We have large backgrounds. And there are also uncertainties in the dark matter distribution around us. So what is the dark matter distribution around us or in the solar neighborhood? So if you consider the position of the sun, we want to know how much dark matter there is, what is the density and velocity distribution of dark matter around us. So usually, the simplest thing to do is to consider a simple theoretical model for the dark matter distribution in our galaxy, and this is called the standard halo model. So this assumes that the dark matters are distributed in a spherical halo, and of course they're collisionless, and also their velocity distribution is isotropic. So at different directions you look, they have the same velocity distribution. Now, in this model, so again, this is just a model. We have to test it against something to make sure that this is the correct model. But in this model, the density of dark matter goes as 1 over the distance squared. So in the center of the galaxy, the density is the maximum. And as you go to larger and larger distances from the center, so to the outskirts of the halo, the density just decreases as 1 over the distance squared. The amount of the dark matter around us, so the local dark matter density, and this is in this specific units, but I'll explain what this is. So this is 0.3 giga electron volts per centimeter cube. So the mass of the proton, if you want to compare, is 1 GeV. And so this means there is less than the mass of a proton in every centimeter cube of volume. Okay, so the dark matter density is less than the mass of a proton in every centimeter cube. But to just be able to compare a little bit better to what we, macroscopically see, if you consider a coffee mug, this is on average about 1 dark matter particle per coffee mug. So this depends, of course, on the mass you're assuming for dark matter, but let's say the WIMP masses, this is on average about 1 dark matter particle in your coffee mug. So this is the amount of dark matter that in the standard halo model you assume. And there are ways to try to measure this density of dark matter. And actually, there has been a lot of measurements for this. And so we can check if this is a correct assumption or not. So there are 2 main ways to make these measurements of the local dark matter density. So the first one is called local estimates, where you measure the velocity of nearby stars, and then you can constrain the gravitational potential at the position of the sun. And so you have to know how many stars and gas, what are the densities of gas and stars close to us. And then you can deduce the density of dark matter close to the location of the sun. Another way for measuring the local dark matter density is using the rotation curve data, which I mentioned to you at the beginning. And for this, you have to actually theoretically model the mass of the Milky Way, both the visible mass and the dark matter mass, not only at our local position, but at different radii. And then fit to this rotation curve data, the velocities of the stars and the gas, and then you can deduce the dark matter density around our position. And again, these measurements for the dark matter density has a very long history. So already in the 1920s, there was this Dutch astronomer called Kapteyn, and he used the measurements of vertical velocities of stars near the sun, and he calculated the local dark matter density, and he came up with this number. So it's 0.285 GeV per centimeter cube. And actually, considering all the measurements happening after that until today, we have, based on the type of measurement that is done and the assumptions which go into each measurement and the data used to make this measurement, this is the range we have for the local dark matter density. So Kapteyn was not off really. It was maybe on the lower range of the value, but we know the local dark matter density by up to a factor of 2. So it's between 0.3 to 0.6 GeV per centimeter cube. And so you expect to have a few dark matter particles per your coffee mug, basically. So we have all these observations of the velocities of stars that we can use to make this kind of measurement for the local dark matter density. But what can we say about the velocities of dark matter particles? So this becomes more challenging because we can't just go to observational data and try to figure this out. It's much harder than just finding what the density is. So in the standard halo model, as I mentioned, the dark matter velocity distribution is isotropic, and this is modeled as a Maxwell-Boltzmann velocity distribution, which is shown here with this curve. And this is basically showing the number of particles as a function of their velocity. And so the most probable speed of dark matter particles in this model is 220 kilometers per second. So this just means that most of the dark matter particles are moving with this speed. But how can we obtain information from cosmological simulations actually about the local dark matter velocity distribution? Because again, as I mentioned, with observations alone, this is a difficult task, but we have all these galaxies that are simulated galaxies, which look a lot like our own Milky Way. And we can, in principle, just go to those galaxies. And if they mimic the Milky Way, we can figure out what are the velocities of dark matter particles close to us. So this is showing you one of these simulations called the EAGLE simulations. And this is a cut through a really large volume of this simulation. So this is 100 megaparsec. And if you zoom in to one small section of the simulation and zoom in a bit more, you see a galaxy, which is the spiral galaxy looking like our own Milky Way. So that's the size of a galaxy there. And here you're just seeing all the visible matter in the simulations. And you are seeing that the different colors are just a different temperature of gas in the simulation. So I'm not showing any dark matter yet. This is just the visible matter. And so we can take these galaxies. These are all simulated galaxies. And we have also higher resolution simulations. So we have, we can produce many galaxies which look a lot like the Milky Way and find these so-called Milky Way analogs in the simulations. So they have a number of properties that the Milky Way has. They have the mass of the Milky Way. They fit the rotation curve data of the Milky Way. And so they're good analogs for the real Milky Way. And so how can we find now the velocities of dark matter particles in these simulations? Well, what you need to do is to consider a region close to the solar circle where we believe the sun exists. And then you can just measure in these simulations the velocities of the dark matter particles in this region. And you can figure out how many particles are moving with 220 kilometers per second or other velocities. And the result that we find from this sort of study is interesting. So this is showing you on the right the same velocity distribution I showed you before, but now for two of these simulated galaxies. So one of them shown in green actually has the maximum speed at 220. This is the most probable speed, very similar to what we believe is the number in the standard HALO model, is a theoretical model. But then there's another one, which is shown here in magenta, and this has a much higher most probable speed. So there is a range of the most probable speeds, and these two galaxies shown with the results shown in green and magenta are both Milky Way-like galaxies. So they fit a lot of the properties of the Milky Way. So there is a range of dark matter speeds, that's most probable dark matter speeds that you would get from simulations. And so this would actually also change if you do have some positive signal in one of your experiments and you want to try to figure out what is the mass and what is of dark matter and what is its interaction strength with ordinary matter. These numbers, which are different than what people assume theoretically, would also change that determination. So it would change the particle physics information that we can extract from the experiment searching for dark matter. Now, in the last part of the talk, I also want to talk about other signatures of dark matter. And one of these other signatures, which is quite important, we can actually go to astronomical data to look for this signature. So here you see a map of the Milky Way, and this is produced by the Gaia satellite, which is this European space satellite, which really revolutionized our understanding of the Milky Way by measuring the velocities and positions of more than 1.8 billion stars in our galaxy. So this is really an extreme amount of data and information that we have from the visible parts of the galaxy. Now, one of the interesting things that was discovered in Gaia data was a number of stellar streams in our galaxy. And so you see these streams here plotted in different colors in this image. And these are just basically, these streams are formed when you have a dwarf galaxy, a small galaxy, or a globular cluster, which are disturbed by the potential of the Milky Way. And so their stars are actually stripped and they are positioned in these orbits around the center of the galaxy. And so why is this important for dark matter? So the reason is that this is, again, only all this picture I'm showing you is the visible part. And you can consider this, again, as showed before, you have the halo of dark matter, which is surrounding this visible part, and you have actually all these substructures, subhalos, which are there as well. And so the idea is that many of these subhalos are just moving around the center of the galaxy, and they can get close to one of these stellar streams, and they can gravitationally perturb the position of stars in this stream. And so they can produce some gaps, or they can pull or push, the stars which exist in these streams. And all these features can be detectable in Gaia data and also in future astronomical data. And so this is a way to inform, to figure out and infer the amount of dark matter and the masses of these subhalos from what we would see as perturbations in these stellar streams. So to show you an actual example of an observed stream, this is the GD1 stream, which was observed in Gaia. And you see on the upper panel the positions of the stars in this stream over the sky. So you already see, when you look at this upper panel, that there are some gaps in the stream. So you would expect the stream to be rather smooth, but there are some features in this stream, some perturbations of the stars. And if you take a smooth stream where you have stars just located, let's say, just smoothly along the stream, and you simulate the perturbation due to the effect of a particular subhalo with some particular mass coming by. So this is a dark matter subhalo or clump coming by. You can see the effect in this bottom panel, where you really produce something which looks a lot to like the observed GD1 stream. So this is somehow hinting to us that maybe all these perturbations and gaps and effects that we are seeing in these streams are due to some subhalos flying by the stream. So this can give us a lot of information about the masses of the subhalos, dark matter subhalos, and the properties of the dark matter subhalos and their distribution in our galaxy. So this whole kind of research that we are doing is very similar to maybe what ancient explorers did long time ago when they were trying to map the world. So this is actually an old map from 1560 by Paolo Forlani. And this is the first map that had the word Canada actually printed on a map. And so the same way that these explorers many centuries ago would just travel and look for unknown territories and discover some things that they would not even imagine, we are doing the same thing, but with dark matter. So we're trying to map the dark matter distribution and use this map to gain information about the actual nature of the dark matter particle. And in this sort of journey, we are sure that we're going to see something really exciting, and maybe we discover something that we did not even imagine before, and that's how science works. So to conclude, dark matter has not been detected, and we don't know what its nature is, but there is really a huge worldwide theoretical and experimental effort underway to unravel the nature of dark matter. And in this effort, we are using state-of-the-art cosmological simulations to shed some light on many properties of dark matter. We're using astronomical observations, and we are also using data from multiple dark matter searches. And these all go together, in really a multidisciplinary way to help us identify the nature of the dark matter particle. And I think really the next generation of experiments, upcoming observations and simulations will help us unravel the dark matter mystery. Thank you very much for your time.
Thank you very much. Yep. All right. Looks like we're up and running here, folks. And we'll start off by saying, of course, thank you very, very much to Professor Bozorgnia for giving me and probably quite a few other folks something extra to think of over our morning coffee cup. Wow, the area of dark matter has advanced so much over the years. Galaxies, cosmic microwave background, and gravitational lensing, all this evidence of dark matter. And you even had the Snow Lab, which is just next door in Sudbury, Ontario. So I suppose we should wave to our dark matter neighbors over there. And your topic has certainly illuminated this topic quite a bit. Sounds like there are still plenty of mysteries out there to investigate, though. We have got lots of questions. I've been looking over in chat, all kinds of things coming your way. We might not be able to get to all of them, but we will be able to take probably about 10 minutes worth. So I'm actually going to pass over to Blake for questions for our speaker now. Yeah, no worries. We just seems like we're having a few problems with sound here. We'll just hopefully get Blake back in just a second. And of course, I'll go ahead and call out that this was really, really fun. I'm always happy to see, of course, the observational evidence. I loved the picture of the streams in particular. So hopefully I we'll be able to get Blake back in relatively quickly to get those questions from chat. But maybe while we're going, since the streams did appear, I saw the Sagittarius stream in that last picture. We could even talk a little bit about the lovely halo of the Milky Way. As Professor Bozorgnia mentioned, the halo is, of course, sort of probed by these streams, which are of great interest to me and a lot of other observational astronomers. But it does have these kind of different areas. Can we maybe get Professor Bozorgnia back on to chat about the shape of the halo of the Milky Way?
Yes, so the halo of the Milky Way itself, so if you consider the smooth part, again, we believe that the density of dark matter is the maximum in the center, and it would decrease as we go to the outskirts of the halo. And the inner halo itself, you can try to obtain information about the shape of the inner halo up to 5-10 kiloparsecs, where we are at 8 kiloparsec. The sun is at 8 kiloparsec. And we can go to cosmological simulations to figure out what is the shape of this inner halo. And some maybe older simulations which were done only including dark matter. So these were dark matter only simulations. They pointed out that the halo is triaxial. But the newer simulations, which include both dark matter and ordinary matter, all the astrophysical processes, what they all show is that the inner halo is close to spherical. And as we get maybe to larger radii, then there's more of a deviation from spherical symmetry. But the inner halos at the position of the sun, the halo is very much spherical.
Wonderful. Thank you so much for that. It is, of course, one of my favorite pet topics, but maybe we shouldn't talk about that for too long. While we're waiting, we'll try Blake. All right, let's try Blake one more time and see if we can get him back. Yeah, all right. So it looks like we are so sorry for Blake. We are apparently having a bit of problem with sound on that end, but I am just going to go back up to some of the questions that Blake marked earlier. Now this is not necessarily in order, so bear with me here. But a question from Douglas: if dark matter reacts to gravity, can dark matter form black holes? So I hand this off to our wonderful speaker.
So that's a very good question. So dark matter, so the usual black holes that we know are formed from stars, they need actually ordinary matter to form. But of course, dark matter can accumulate in the black hole, in the center of our galaxy, for example. But they would not be forming in the first place these usual stellar black holes, astrophysical black holes. Now, you might imagine that there are black holes called primordial black holes, and these are black holes which were created in the first second after the Big Bang. And so these black holes, these are hypothetical yet, of course, but they can be part of the dark matter abundance. All the constraints we have for the existence of these black holes tell us that they cannot be all dark matter, but they can be part of some percentage of dark matter.
Wonderful. And looks like we've got a question from Ben as well. This one's a little bit detailed, but Ben read last November about the galaxy NGC 1052 DF4, which has got quite the name there, and was apparently missing its dark matter or black matter. It was maybe stolen by another galaxy, NGC 1052. Have you heard about this or have any comment about it?
I don't have any particular comment about this particular galaxy, but you can think of, well, first of all, you have to make sure that those statements are accurate. How was it determined that this galaxy doesn't have any dark matter? And so there's a lot of uncertainties in those kind of astrophysical measurements. So, yeah, I don't have, other than that, any more technical comments for that particular galaxy.
All right, well, that's fair enough. We'll have to look that one up maybe a little bit more. Now, it looks like we have another question from Cicely, I hope I'm saying the name right, about the bullet cluster, which was an absolutely lovely picture in your talk, asking, is there no dark matter between clusters with the hot gas?
So there is dark matter, right? But it's very small amount in between. But you can think about if you, let's go back to maybe this picture, which shows a larger scale, and you have, this is gas, it's not dark matter, but you see these filaments. And also, if you go to this, the dark matter part, you would see something very similar. So there are these filaments of dark matter in between galaxies and clusters of galaxies. But the majority of the dark matter, the majority of the main densities in the inside the cluster or inside individual galaxies. So that is why you actually see you see that separation as well in those galaxies and the other galaxy cluster collisions. And the other reason is actually dark matter has moved very fast, so it is not interacting electromagnetically, so it was just free to move away from those central parts of the two galaxies colliding, whereas the gas had slowed down. So that was another reason that you wouldn't see the dark matter in between where the gas was, basically.
Wonderful. Okay, so we have a question from Lou just following that up. And I actually just want to go ahead and put a quote as well that came out, quote unquote, this talk is awesome. So very, very nice, very fun. And Lou asks, could supernova create the additional matter or this additional matter?
No, again, going back to what dark matter is and how it behaves, we need something, some particle, let's say if we believe dark matter is a particle that is neutral, right? And is also stable enough and is also massive. So all those properties has to be there. And for example, supernova produce neutrinos, which neutrinos actually do satisfy some of the conditions that dark matter should satisfy. So it was believed for a while that neutrinos maybe can be the dark matter candidate, but actually their abundance is not enough. So they're much, much less than what we need for the dark matter in the universe. Another reason is that they're moving too fast to form structures. So you need something to be massive and have a higher mass and be slow moving, basically, to form the structures that we see in the universe. So they can't be dark matter.
Okay, well that definitely helps. Well, we know what it isn't, maybe. Now there's another question actually from Blake in relation to Snow Lab, actually from before. But some RASC Toronto and Aurelia Astronomy Club members actually got to go to Snow Lab in 2012, so I'm really jealous. The question is, you mentioned Super CDMS is being commissioned. Are there other experiments planned there that you know of?
Yes, so here I list actually in this map, if you look under Snow Lab, this is all the experiments which are searching for dark matter, and they're taking data and very, interesting on their own. I mentioned Super CDMS because it's really one of the next generation of direct detection experiments, so it's very exciting, and it's supposed to, search for the parameter region, of mass of dark matter and its interactions constraint with ordinary matter that hasn't been probed yet. So some of the other experiments are at some region which are already being probed by all the various experiments around the world, whereas super CDMS will focus on lower mass dark matter particles and at masses which have not been probed yet. So this is really exciting time for SNOLAB and results from super CDMS coming out.
Wonderful. Thank you so much for that. And yeah, lots of comments actually, and compliments in the comments, I should say. So I think you actually answered the neutrino question along the way here. So not being too much, I'll go ahead and skip that one and go over to one of the really fun ones. Can the energy produced in by dark matter be used as a source of energy for space travel?
That's another fun question. So far, we don't know, first of all, well, what dark matter is. We know what it isn't. So I guess maybe after detecting the actual dark matter particle, we might be able to think about how to use particular properties for other applications. But if we think that dark matter is made of WIMPs, the energy that it would have, in the lab is not so high. So it's kilo electron volt energies. And so, this is just enough to make a nucleus in an underground laboratory just to move a little bit. If it's in a crystal or lattice, it makes it move a little bit and produce heat or phonons or some other signals like ionization or charge, but it's not enough to do anything else with it. But again, dark matter can be something else that we haven't thought about, or one of the other candidates. And so this is something that this is definitely in the future. We can start thinking about applications after dark matter is discovered.
Wonderful. So we do have one more. I think we have time for just a couple more questions here. We might not get to all of them, but a lot of interesting ones. So Norman has a question. Why does a dark matter particle have to be a particle, or does it? Ordinary matter is made of many kinds of particles. Why not dark matter? And this is a comment, a member of Sudbury Rask. So hello, Sudbury.
That's definitely a possibility. We saw that the standard model of particle physics is quite complex with many particles. So we can think that dark matter is not only one particle, but it is made of some dark sector, which we have many different particles there similar to the standard model. On the other hand, it might not be a particle at all. It might be some massive objects like a primordial black hole. So again, all the constraints we have from observations. So for example, we can look at the motion of stars. And if we have many of these primordial black holes going by, it would perturb the motion of stars. So we have some constraints on how much dark matter it could be in this form of a compact object like a primordial black hole. But of course, again, uncertainties in some of those constraints also exist. And this has been really an active field which has been changing very rapidly. So it's definitely still a possibility, and it does not have to be a particle. This is just one of the scenarios that we are considering and really looking and searching for dark matter, searching at one very specific candidate of dark matter, but it could be something very different. And in many years from now, if this doesn't work, we'll definitely look at other candidates, and the possibilities are always open. So it's very exciting to explore.
Indeed, endless possibilities, as it were. Looks like we have time for another one, so I'm going to go ahead and ask the question from RP. So how are scientists able to estimate the mass of dark matter from the map of the cosmic microwave background?
So in the cosmic microwave background, the map that we have, we are seeing the temperature fluctuations there. And this is a measure of the small density fluctuations which existed at that time, at around 400,000 years after the Big Bang. And since regular matter, the ordinary matter, has electromagnetic interactions, it has a very different behavior than the dark matter, which has only gravitational interactions. And so by really looking at all the details of these fluctuations, and we at different angular scales, we can actually figure out the amount of dark matter very precisely, and also the amount of dark energy and ordinary matter, and the curvature of the universe. So a lot of information from all these tiny fluctuations, which are really 1 part in 10 to the 5. These are really tiny fluctuations, but it really contains all that information because of the different type of interactions of dark matter and properties of dark matter compared to the ordinary matter.
Wonderful. Well, I guess I'm going to go ahead and say thank you once again, Professor Bozorgnia. We certainly could stay here quite a while chatting. In particular, I'm sure I could bend your ear about the Sagittarius stream for an enormous amount of time. And I'm going to go ahead and just say again, thank you so much for tonight. And we're going to hand over to our president of the Toronto Centre RASC, Tom Luton, to actually finish off our evening tonight. So we'll go ahead and start that handoff process now.
Thank you very much, Elena. All right, well, good evening, everyone. I hope you enjoyed our talk. So let's just get the announcements underway. So we've got 2 types of meetings here at the RASC Toronto Centre. We've got our speaker nights, which you've just seen. We also have our recreational astronomy nights, which next one will happen in 2 weeks' time. Both of these are broadcast live over the internet. If you happen to be here, please say hi in the YouTube chat, enter some questions for the presenters. If you're a new member, please introduce yourself. And if you're from far, far away, let us know where you're from. Our next recreational astronomy night is on the 3rd of February, 7:30 p.m. Arnold Brody will be covering the sky this month. Artash and Arushi Nath will be discussing do-it-yourself asteroid astrometry using Python. And Blake Nancaro will be discussing weather forecasting resources for amateur astronomers here at youtube.com/RASCToronto/live. If you'd like to present something, folks, give a shout to our very own Paul Markov. Our next speakers night is the 17th of February. Professor Hildig Nielsen will be discussing Indigenous astronomers, stories of the sky, and indigenizing the Drake equation. A little shout out to our joint RASC Royal Canadian Institute lecture, which will be coming up on the 28th of February. Professor Keith Vanderlyn will be discussing strange signals, fast radio bursts. You're going to have to register for this one. Please visit the link to register. So Toronto Centre is famous for our educational and public outreach activities. Unfortunately, all of the live interactions are shut down due to the COVID outbreak. We are planning virtual star parties and EPO talks with the Ontario Science Centre, with Millennium Square, the David Dunlop Observatory, the St. Clair O'Connor community, the Dunlap Institute, with Brownies, Cubs, Scouts, and school groups, as well as the new Observers to Visual Astronomy. Please contact public education at rascto.ca for more info. Our observing sessions are suspended until further notice due to the outbreak. At Bayview Village Park, the Long Sault Conservation Area, and the Ontario Science Centre star parties are all shut down. Also, the Carr Astronomical Observatory, our club observatory in the Blue Mountains, is closed until further notice. It is also winter, so the road is full of snow, which is a bit of a problem for most folks as well. We're currently in a maintenance-only mode. As the last few slides have suggested, we do a lot of volunteer work. So we require volunteers even in these quiet times. So if you're a RASC Toronto member, if you're interested in helping, if you've got any free time at all, please drop a note to our volunteer coordination team at volunteer@rascto.ca. We've got a job posting open. We're still looking for a new head of our Light Pollution Abatement Committee. If you're environmentally conscious and you're looking to get involved on a more casual level, please drop us a line. It comes with a really cool job title, Prince or Princess of Darkness. Our Stellarium training continues. Software courses, our level 1 course, February the 22nd and March 1st. Courses are full, sorry. We've got a waiting list as well. We've got more courses planned, levels 1, 2, and a level 3 course, plus Stellarium for educators. Click on the link for more details. This is the part where I get to plug membership in the RASC. So you can renew or join up for the first time online at secure.rasc.ca. As we all know, COVID has thrown a lot of people into some financial trouble. If you really want to be a member, you can contact our RASC head office. We do have a RASC emergency fund. It is completely confidential. You can also acquire a gift membership. Speak to Adela at the national office at mempub@rasc.ca. We've also got some products to plug. Our famous Observer's Handbook has been mailed out to our members. If you're not a member or you want to get another copy, excuse me, they're for sale on the RASC e-store. Our observers calendar, we are not having any in-person sales this year as due to the COVID outbreak, so they are available from the RASC e-store as well. And with that, I want to wish you all a very good night. I want to thank you very much for joining us. Please follow us on social media, and please like and subscribe and click the notification bell for further YouTube videos. And on behalf of the center, be safe and keep looking up. Good night, everybody.